Hi, I'm Alan Lowe, software architect and P4 lead at Nvidia. Welcome to the 2022 P4 workshop. Today, it's a pleasure to introduce Anjali Jain, Namrata Limaye, Nishanth Bhat from Intel's networking group, who are working on the IPU for packet processing, LAN, and virtualization. In their presentation, connection tracking using P4, they will discuss this important stateful IPU use case and how IPU hardware blocks can be programmed in P4 to handle connection tracking from establishment to teardown. This talk will cover both connection-oriented and connection-less flows and end with a small demo of an important P&A functionalities such as add-on miss on a real hardware target. Thank you for joining us today. It's all yours.
Thanks, Alan. Hi, I am Anjali, and with me I have my Intel colleagues, and hopefully Hari could join a little later, who's from Google. This is a collaborative work that we have done with Intel and Google for the Intel IPU, which is Mount Evans. Although what we are presenting here applies to any target that is P&A compliant, which is soft target, as well as the IPU, which is FPGA based or ASIC, or even the switches that we have. So what is connection tracking? Connection tracking is a feature that is deployed quite extensively in the data plane in a data center to track individual flows and allow for stateful operations on the flows, such as stateful firewalling or logging or access control, different pay-per-use kind of SLAs and stuff like that. And then there is also for various security aspects like avoiding simple attacks or making sure there is no malicious packets coming in during the flow, such as something which is out of a window check for sequence number in case of TCP. Again, as Alan mentioned, this is both can apply to stateful connections or flows like TCP, or the stateless ones like UDP. We'll try and focus more on the TCP one, just so that as it is more complex. Okay, so yeah, so what I am going to talk about is connection tracking, as I mentioned, and in this picture, you can see there are two basic ingredients for connection tracking. One is the stateless firewall piece, and the other is the stateful firewall piece. The stateless firewall piece is related to network policies like matching on port ranges, or matching on exact match IP address, or wildcard matches, or LP matches for subnets or whatnot. And those policies could be directional, and there could be a trusted direction and untrusted direction. So the connection could be allowed to start only in one direction, and once it is started, it can be allowed from both sides. So connection tracking in this example is used as an ability to puncture holes into your firewall just for the right connections to come in, and for the duration that you want it to be allowed to come in. And so once the flows are checked against the stateless firewall policies, and if there is a hit in those policy and the flow is allowed, then hardware or the target, the P4 target, adds that rule into the stateful firewall table, and if logging is required, it would also have actions to log the first packet of the flow. If it is not allowed, it will still check in the stateful firewall table to see if the connection is already been established, and if it established, then the packets are allowed. And if they are not, the flow is not already added, and it is coming from an untrusted direction, and of course there's a miss in the stateless firewall rule, then of course the packet, the flow is not allowed and it's dropped. So Yeah, so it's quite simple as it looks like, but of course to implement that for millions of flows and to maintain all the state and everything, it's quite an interesting problem. So this picture, can you go to the next number? Sorry, I'm looking at my screen. So yeah, so virtual forwarding plus stateful firewall example. This picture just shows very simple. There's a forwarding table right in front, and that would match on the outer IP address and VNI from the tunnel or something, and then decide where it needs to be forwarded based on the virtualized environment that we are in. And then you could have the three layers of different kind of stateless policies, and then finally your firewall connection tracker table, which is a flow rule, and that can be aged out based on aging times and things like that. This basically says that even though we define this whole thing for a given target, we have to also keep in mind that the connection tracking that happens for a virtual machine, the virtual machine can be migrated, and so you have to have the ability from your before runtime folks to be able to retrieve all the flows that hardware added to be able to transmit to the destination just in time, so that you avoid something called as the black hole effect, which basically means that if the VM starts off on the destination machine and it tries to send packets towards the flow that was established in the source, if the flow cache firewall policies are not reinstated on the destination, that it would experience a black hole and it cannot reach the VM once it is migrated. So to avoid that, of course, you have to make sure you prepare the destination VM with carrying forward all your flow cache stateful policies over to the destination machine. So yeah, so the P4 runtime has to then support, even though the hardware is adding the rules or removing the rules, but we have to be able to read them and restore it on the destination machine from software. We can go to the next slide. This slide is basically kind of a little bit more detail on how the target kind of deals with these flows. These flows run in millions, so typically the most targets would deploy that in two-tiered caches, L1, L2 cache, something on die, and the rest of it all on the DDR backup memory. The hardware has to support certain timers so that you can have when the connection is getting started, you're in one state and you want to have some absolute timer there so that the connection established state does not last for certain amount of milliseconds or seconds. And once it's established, it could have a longer timer to kind of be in a replenish mode where every packet that comes in replenish the timer so that you have the next extra 10 minutes or 15 minutes or whatever to keep the connection alive. So every new packet that comes in replenishes the timer. And then there's the teardown, which is again absolute. There is also one more part to kind of mention here is that even though the teardown would be an absolute timer, with millions of flows and the add rate that these devices have to support is very high, like 10 million per second, or definitely millions per second flow add rate, right? So I've given a couple of examples as to like how many stale flows can exist if you don't if you just rely on the absolute timer to kind of remove these flows, and that absolute timer is in say milliseconds, 200 milliseconds, it would be this amount of stale flows, or if it is in seconds, it can be a lot more amount of stale flows, and that's why you have to have more advanced data plane implementation where you can remove the flow rule immediately based on sequence number match. And that's something that we would come back with the flows for that.
Thank you, Anjali. So we have been working on the infrastructure recipe pipeline. And here is the TX side of it, the egress VM to wire side of it. This pipeline is basically called Linux networking pipeline, and we are going to open source it pretty soon for P4TPTK on IPDK website. So we have the control plane blocks here, which are programmed via TDI. So some tables you'll see are programmed from the TDI or the P4 runtime. And then we have the gray blocks that are programmed from the kernel directly. So the packet coming in, so basically the netlink notifications from the kernel are translated into the P4 tables, and the P4 pipeline is programmed here using kernel. This is the CT block in between, and I'll go over the flow now. So if it's an ART packet and it needs to go up to the control plane path, which is obvious for us, and this table is basically maintained, which contains the V4 to VLAN mapping, and it sends it up to the host or ACC. So here we can send ARP or any other kind of control packets up in the stack. And also we have, if there's an IV packet coming in, since this is the TX direction, this packet will need to be encapped. So there's this L2 forward tunnel table, which encaps the packet and determines the port to send out to. Next, the packet will go through this pipeline into the L3 routing table, which is a fixed policy. Here it determines the next hop or goes into the hash block for ECMP, where the ECMP table determines the next hop in that case. We also have a CT working in here. So CT, there are three tables. Port table is an example here, which is the fixed policy. Here, port table can say it's a range table, so it can say, this is the range of the ports that are allowed or are supposed to be dropped in the CT flow, and this sends the packet to the CT state table. So the CT state table basically switches the packet based on if it's a send flag or if it's a reset flag or a fin flag or a SYNAC, if the connection needs to be established or not. In the case where it's a send flag or a SYNAC flag and the connection needs to be established, the flow is auto inserted into the CT block here. This is a PNA construct, and we've added the auto add capability in the PNA. So we are using that here. So the CT state table will determine if the flow needs to be added and a timer needs to be started in the CT auto add table. And in the CT auto add table, using the auto add capability, a 5-tuple can be added in this table. So this table is basically common in TX and RX directions. So the SYN flag in any direction can be processed and a flow can be added, and the other direction will work as how the connection tracker works. So from here, the packet goes into the hash block and into the ECMP, where the next hop is determined. Your next hop table, these tables, as I said, are driven from kernel programming. So this next hop table basically determines the outer source MAC test. And in between, we have an exception table. So if there is a miss, this exception table can be, the packets can be sent up to the host using this exception table and into the P4 runtime controller. Or if it's successful, then the packet will go out to the wire. So this is the infrastructure recipe pipeline for the TX direction. The RX looks very similar, except that the packet is going to the VM here. So the packet needs to be decapped, and there's no routing in this case. So the ART packet, as is, will use the control plane table and send the packet to the port netdev into the VLANs, which are hooked into the OVS for our case for ART processing. And then the IP packets here are supposed to be decapped. So this will go into the L2 forward tunnel decap table. And then the packet is going to go in the connection tracker again, where there is a port range table, which is a fixed policy in the RX direction as well. And the CT state table. So the CT state table will determine if the packet is in SYNAC or ACK or reset or FIN, and will adjust the timers based on that into the CT auto at table or add a new flow to enable the connection tracking entirely in the hardware. So here, as you see, there's no packet needs to go to the software for CT processing. It's all handled in the P4 data plane in the data path pipeline using the auto insert capability that PNA has added. And then from here, the packet is forwarded to the exception table or straight to the PM. I have the P4 tables here that will show how the P4 actually works in how the connection tracking actually works in the P4. So we have the set CT options here, the state table, the CT state table that I had in the picture before, and which matches on the direction and the TCP flags. And based on if the flag is a SYN packet or a FIN or a REST packet or any other packet, it will perform the necessary actions. So for the TCP SYN packet here, we basically set the add-on miss metadata to true, which will be used in the next CT table, the 5-tuple table that we have, to insert the to auto add the flow into the table. And then the expire timer is set to a small timer, which is the TCP new timer. And this timer will basically get expired if we don't see the SYN-ACK or ACK packets. And then we have the FIN or REST packet processing, which is action, which basically does not do an add-on miss, and will set the timer to now, so the packet is expired right away. Other packets will set the timer to the established state. The flow is already added here, and because the SYN packet was the first one to arrive, and the timer is basically changed to a long timer here. The next tables the next table is the CT TCP table, which is the actual table that goes into your exact match. This is a 5-tuple consisting of source address, dest address, protocol, and source port and dest port as the keys. Here, select by direction and PNA direction P here is our PNA constructs. The net to host and host to net is the direction flag that PNA specifies. And based on the direction using this function, we can select whether we have to match first on the source address or the dest address. So that is why. So this is how we can use the common table in both directions. This table has 2 actions: TCP table hit and a miss. We have some flags that are defined in PNA, add-on miss flag, which basically says that this table is capable of adding a flow on miss, and the idle timeout with auto delete flag, which basically it will expire the flow automatically if on the expiry. And then the default action is TCP table miss. So when a packet comes into this table, it will first miss because the flow is not present, and we'll go into the TCP table miss action here. And if we have so on the SYN packet, we had already set the add-on miss equals true. So here this condition will match, and basically the auto insert of the flow will happen here using add entry with an action TCP table hit. So the next time the packet comes in, it will match the flow, and it will execute the hit action. And here in the hit action, basically this is refreshing the timer because it's seeing a packet coming in. So either if a new value of the timer is specified, it will update the timer and then restart the expired timer. So this is basically how the connection tracking is working in the P4 data plane. And next we have the demo of this P4 on Mount Evans emulator, and Nishanth. And Nishanth is going to show the demo after the next slide. So this is the code template and website information. Here we have the PNA connection tracking information. This is the PNA TCP example for connection tracking. And then we have the data plane. So this infrastructure P4 that I have shown is going to be open sourced on GitHub very shortly, about in less than a month. This will be working for P4D PDK target, and this is the link of where you can find this this P4. And TDI is used to program from the P4 runtime. The link for TDI APIs is here in the third point. And for future improvements, we'll have the fast closure implemented and immediate removal of flows. And the new tables will be added to do the sequence number match in the removal state. So handing over to you, Nishanth, please take over.
Yeah, thanks, Namrata. So this is the network topology which we'll be using to demonstrate the connection tracking use case. So we have a host server here, which is connected to the Mount Evans IPU. And to program rules to the IPU, we'll be using the P4STE software stack. So basically, the STE provides us with a CLI client utility, which will help us add rules to the hardware pipeline. And the low-level drivers will help program this rule to the hardware. And to demonstrate the packet flow through the packet processing pipeline, we'll be using the physical port on the Mount Evans IPU. And on the host side, we'll be using a generic LAN interface to demonstrate the packet flow. So the P4 program overview, as Namrata explained, we'll be using these two tables. So the first table, which is set city options, will be programmed by the control plane to match specific TCP flags like SYN packet, FIN packet, reset packet, or other TCP packets. So this will be programmed by the control plane, and the match fields will be the flags in the TCP header and the packet direction metadata. And the other table which we'll be using is the CT-TCP table. So this table will not have any involvement from the control plane because it's a add-on miss table. So it will auto learn the entries based on the packets which are hitting this table, and it will execute either the table miss action for the first time it sees the flow, and for subsequent packets of the flow, it will execute the table hit action. So the scenario is we'll be using the same P4 program, which we just Namrata explained, and we'll be using the physical ports on the network side, and a LAN generic interface will be used on the host server side to demonstrate the traffic flow. And we'll be using some standard utilities like SCAPI, iperf, and TCP dump to verify that traffic is flowing correctly. So for this use case, we are using the P4C compiler to compile the P4 program. And we are using the CPT tool to generate the package, which will be loaded on the Mount Evans IPU. And certain artifacts will also be generated. So one of them is the TDI JSON, which will be used by the IPDK software stack. So this is completely target agnostic, and it will be used to add rules to the packet processing pipeline. And this is what the rule configuration looks like for the set city options table. So all these flags correspond to different TCP packets. So the first rule corresponds to the SYN packet, and the next two rules correspond to the TCP FIN and TCP reset packet. So these are the only three rules which will be adding to the pipeline. All the other table, which is the CT-TCP table, will auto learn the flows and forward the packets accordingly. So let's jump to the demo. So here I have a Mount Evans simulator. So here, the top right, I have the CLI client, which I'll be using to add rules to the pipeline. And on the top left, I have a virtual machine, which will help me send packets to the physical interface of the Mount Evans IPU. And on the bottom right, I have the generic LAN interface on the host server side, which will be used to send and receive packets on the host interface. So we'll be using these interfaces to send traffic. So let's go ahead and add the rules to the set CT options table. So we'll be adding these 3 rules corresponding to the TCP packets. So the rule addition is successful. Now we'll go to certain scenarios. So according to our P4 program, the auto learning of flows happens only in the RX direction. That is when the packet flows from the network to the host direction. So we'll verify that if it's working well. So for this, we'll be using the iperf tool. So on the host side, I'll bring up the iperf server, which is listening on port number 10,000. And on the network side, I'll be running the iperf client, which will try to initiate a connection with the iperf server on the generic LAN interface. So we can see that the connection is successful. So the connection is going through because first it sends a SYN packet during the TCP handshake, which matches the rule which we have added in the set city options table. And for further forwarding is taken care by the add-on miss table, which learns the flow and helps in forwarding the packets. So you can see that the client was able to connect and forward packets successfully. The TCP connection has come to a close. So this is the first scenario. Now we'll go to the TX direction, where the set city options table is not applying in the TX direction. So when a connection is initiated from the generic LAN interface to the network side, we should not see the connection establishment happening. So let's use iperf and verify that. So we'll bring up the iperf server on the network side, which is listening on port number 20,000. And the iperf client will be running on the generic LAN interface. So you can see that the connection is not going through. We can also verify this with the help of some statistics. So here we have some stats. So we can see that the egress discard packets currently is showing 83. So now let's send some packets using SCAPI and verify that the packets are actually getting discarded. So I'll send some SYN packets from the host to the network direction. And you can see that I've sent 10 packets here, and none of them were received on the network side. And when we check the stats on the Mount Evans, we can see that the egress discard packets has increased from 83 to 93. So the 10 packets were discarded because the flows were not auto-learned. So this is the second scenario. Now we'll jump to the third scenario, where someone tries to send TCP packets without a proper handshake, right? So he's just sending some acknowledgement packets without any handshake prior to this. So even in this case, the flow will not be learned, and any packets which are sent will be dropped. So I'll be initiating this from the network side, and on the LAN generic interface, I'll be using TCP dump to check if the packets are received or not. So I'll be sending 10 packets here again from the network to the host. So I've sent 10 packets and none of them were received on the LAN generic interface. Coming to the stats, we can see that the ingress discard packets have increased by 10. So earlier there were 65, now it's increased to 75. So we can see the connection tracking working. So only if the TCP connection starts with a proper handshake, the flows will be auto-learned and will be allowed through the Mount Evans IPU. Otherwise, the packets will be dropped. So these are the three scenarios which I wanted to demonstrate for this P4 program. And this takes the demo to a conclusion.
Okay, so to summarize, we want to do a connection tracker implementation that's hands-free. That's what Nishanth kind of demonstrated. And we have some more work to follow on with this, which is, as we mentioned, we want to showcase a few other capabilities like the fast flow removal of tables. And then, we do want to take it to the state where this stateful connection tracker can coexist with other stateful features like the stateful load balancer and stuff, where your flow rules that are added could have auto-added actions as well, to count, meter, or even to modify. And then we want to stick to the PNA model for all of this, and that's what we will be publishing very soon. Yeah.
Super, thank you guys. That was a great presentation demo. And I think statefulness is getting a lot of attention now from the PNA community, and it's great to see this kind of progress. So kudos there. I have a couple questions. I'm going to back up to some of the higher level stuff. So as you guys are aware, P4 is basically a stateless language where we rely a lot on externs to maintain state, like encounters and registers. And PNA has made a lot of efforts to add some of this support, and I see you've done a good job of implementing some of those. Can you tell me what are some of the challenges you might have encountered with PNA and or the language in trying to express this use case, and what do you think can be improved in those areas?
Right, so I'll answer this one, Alex. So we did have to add this add-on miss concept, which was not something needed for switches and the PSA model, and I believe this is the single most important thing that was needed for connection tracking. And then you would see this build upon where we have not just add-on miss for the rule, but also add-on miss for the rule with actions and stuff. So that's where it will build upon.
Right.
We do have certain other things in the P4 and PNA architecture that when we do a complete infrastructure deployment, we had to come up with a clean model for certain things which are not classification table. And I don't know if Namrata has another talk where we talk about lookup tables. And so we do use like lookup table in this where we have the mod table and the mod map table. These are lookup tables and not classification tables, where you are just storing a database that you can index and use it from content. So that's a new construct. And as we go along, you would see a few other things which are very specific to a NIC architecture rather than
right.
And yeah, we'll be, this is a start of a journey. We'll see some more coming.
Okay, cool. Hopefully we'll see some of that show up in the PNA forums.
Yes.
Great. Great to hear. So question on some of the scale and performance things you noted. Some like millions of flows and insertion, and you tested some insertion at 100 million entries per second. I wasn't sure this is being done on an emulator or hardware?
This is on a hardware, and
hardware,
this is
okay.
100 million per second. It's 10 million per second.
Great.
Right. So we do support different IP architectures that have a different higher bound of how much rate they can add at. And our top of the class, the Mount Evans, definitely can go to like 10%.
Great. So do you see like future gains in this area, since this I'm assuming this is kind of initial work? Do you see more performance coming out of that?
You would see, I mean, definitely we have tested the boundaries for what the hardware supports. And as we tune our software, there might be some things better that we will see. Definitely, we are going to work on the fast flow removal.
Right.
Which is something that again would be supported at the same rate, because not the hardware does allow for the same rate of removal.
Right.
Yeah. So
okay, yeah, I assume fast closure will give you more capacity.
Exactly. It is a very stuff that we have to keep in mind that If we just rely on the absolute timer for
Right.
closure, then you are blocking a lot of dead flows. The memory is blocked by dead
Right.
flows.
Right.
And so you remove them as fast as possible because your rate of add is so high, 10
Right.
million per second. So in a
Right.
second, yeah, fill up that whole space. Yeah.
Okay, and these numbers are kind of done with just typical iPerf type of traffic, or something a little more
We would go to
sophisticated.
more, evolved, like Chariot or something that
Okay.
we would be using. Right now, this is more of like, we have, we wanted to, I mean, there are so many components involved, starting from the compiler and the runtime and, the software books and everything. So this is more of like, okay, we have everything now, and now we would do some performance demos later. We did do a performance demo for a load balancer. Check that out. Intel's Investor Day and mobile conference. Yeah.
Okay. All right. And another question, and in your abstract, you mentioned connectionless as well. So here's a question. Tell me if it's relevant or not. As you know, UDP is connectionless, but a lot of layer 7 protocols actually use that in a stateful manner. So are you also planning on tracking that in the connection tracking table in some way, or are you saying stateless as in you have stateless policies?
Right. So let me answer it slightly differently. Our hardware is definitely not protocol aware. Right? It doesn't really matter, what protocol you're using. We teach it the protocol, and if the connection ID or whatever defines the session is deeper in the packet, L7 layer, as long as hardware can get to it, the same mechanism can be used for doing connection tracking even deeper in the protocol layers. Again, that's based on the hardware, right? Like whether we want to deploy such a use case, we'll have to work on software models and everything and use cases. Yeah.
Okay, so for now, just TCP, right?
So TCP and UDP for sure, and in UDP, instead of the 3 timers, you will have a single.
Right. Okay.
Yeah.
Okay. Great. Great. And I heard you mention control plane provisioning. At the first, you talked a lot about P4 runtime, and then later in the actual demo, I see we're kind of using CLI with TDI. So can you clarify kind of what your role or goal or roadmap is going forward in terms of control plane provisioning?
Basically, so we have what we call P4 OVS in development, and it's open source, and we are using that for our Linux networking pipeline provisioning, and eventually we want to see that being used for connection tracking as well. So in this demo, we've used TDI, which is another mechanism or APIs that our customers can, call and provision all the tables from there. So we've used TDI here. We could have very well used P4 OVS as well. So different demos are showing different things. There's another demo which is VXLAN with L2 forwarding and L3 routing that Sandeep and Nupur are doing, and that is using the P4 runtime, P4 OVS interface. So this demo we wanted to show the TDI running.
Okay.
Yeah, just
great.
Alan, TDI is table-driven interface, and it is a generic API layer that we are promoting under the IPDK umbrella for all our targets. And you'll see more of TDI discussion.
Right.
Yes. Okay. All right.
And just to add, TDI is open sourced under P4Land.
Okay. So for this use case, did you have to add any specific APIs that like are beyond what's in P4 runtime conceptually?
No. So the only thing that you add is this the state table entries and the port range table that I mentioned, which could be done by add table, simple add table using P4 runtime. And the other table, the CT table, the actual table is actually auto-generated. So there's nothing.
So there's nothing to stop this demo from running on P4 runtime itself.
Yeah, there's nothing.
Okay, great. Okay. All right. Thank you so much for a great presentation. Appreciate your time and efforts.
Thank you.